Good morning again, everyone. This is Philip Griffiths, and the second talk this morning is by Kang Zuo. It's on Hodge theory, Higgs bundle on moduli space of manifolds, and hyperbolicity. Kang, the floor is yours.
Okay, and so today I should talk something about the graded Higgs bundle arising from geometry, and okay, for example, the system of Hodge bundles, and the graded Higgs bundle from the deformation theory. This is the most important. I think this is the most important Higgs bundle arising from the geometry. Then I try to talk about the section 2 and comparison between the deformation Higgs bundle and the system of Hodge bundles. Okay, so let's start. Okay, so throughout we will assume that U is a quasi-projective manifold and compactified by a projective manifold Y bar with the boundary divisor S bar as a normal crossing divisor. And we assume that there is a smooth family over U, just say F from V to U of N projective manifolds. Okay, so leaving out codimension 2 subset of Y bar, we find a good partial compactification from X to Y in the following sense: Y and X are quasi-projective manifold. F is proper and flat, and the U contained in Y and the codimension of Y bar, and without U is bigger or equal to 2, and the boundary divisor S is a smooth, and the pre-image on the F called delta is relative normal crossing divisor over S. Okay, just means that all the components of S and all their intersection are smooth over components of S. Okay, sometimes we call X to Y is log smooth. Okay, so the point is that from X bar from Y bar, from X bar to Y bar could have very singular fibers. We just leaving out some very complicated singular fiber away. Okay. So then following Griffiths and Simpson, we construct the most natural Higgs bundle relating to the geometry and the topology on the family. So we start with the tautologic exact sequence. Okay. So then by take the wedge product, P power wedge product, we get the exact sequence of differential form of high degree. Okay, here the middle is just a grade omega px, which is the quotient of usual P form divided by some subdifferential form from the fibers, and basically from the fibers. Okay, if the base y is just a curve, then the middle term is just the usual P form. Okay, so then we take the direct sum or direct image, EPQ, then which end up with the connecting map, from the coming from the direct image of the exact sequence, form also called the system of Hodge bundles of weight K by Simpson. Okay, E theta in this form. Then we can also construct this Higgs field E theta using the dual of the tautologic exact sequence. Then by the connecting map of the direct image, define the logarithmic Kodaira-dimension map. The Higgs field E theta can be also defined as couple product with the tau. Okay, so now we recall the following proposition, which plays an important role in my talk. So the Higgs bundle E theta is the gradient of the line quasi-canonic extension of variation of polarized Hodge structure on k-spadic cohomology of the smooth family, F from V to U. This theory is well known, and due to Griffiths, he uses the harmonic forms. And today, we present algebraic approach due to Katz and Ota and some more people. It works also over any characteristic satisfying E1 degeneration of Hodge to Dahm spectral sequence. Okay, so let's start to schedule the proof for this proposition. The short exacerbance, okay, short exacerbance, say, short exacerbance 1.12 induces a short exacerbance of complex of log-Differential forms. Okay, so yeah. Right, then we take the case direct image of the sheaf V, okay, as the direct image of the case Dalam cohomology of the relative Dalam complex, okay, which carries the so-called logarithmic Gauss-Manning connection, okay, defined blah blah, okay, defined by connecting map of the long exacerbance, connecting map of the long exacerbance in this way, okay, so. Then we can also introduce the decreasing filtration of truncated subcomplex in this way. We just replacing the usual Dalam complex by setting a zero term in up until to the p-1 places, and then we get the so-called truncated subcomplex. Okay, then we define the Hodge filtration on the V as the image of the natural map from the cohomology of the truncated subcomplex to the Dalam complex. Okay, we just call FP. Okay, so then we look at the connecting map, the connecting map of the Dalam complex is compatible. And which is compatible with Gauss-Manning connection under the natural map induced by inclusion of short exacerbance. So we find the so-called Griffiths transversality. Okay, this filtration satisfy Griffiths transversality, which give us a filtered logarithmic Dalam bundle, right? This F dot satisfy Griffiths transversality. And with the associated graded Higgs bundle in this way, right? Now these things we have the Griffiths transversality. So the quotient of the Gauss-Manning connection become linear operator. This is just called a Higgs field. Okay, so now we look at, since we are working over complex number, the E1 degeneration for Hodge to Dalam holds true. It implies that the map induced by inclusion of the complex is isomorphic. So therefore, consequently, the system of Hodge bundle is isomorphic to the grading of this filtered Dalam bundle. Okay, so by the link, the filtered logarithmic Dalam bundle is a quasi-canonical extension of variation of polarized variable Hodge structure of k-spadic cohomology of the smooth family. So we get the proof, right? We get the proof of the proposition 1.1. Let's make a remark. Denis-Illozy can do something more. This is over a characteristic P, namely given a log smooth family, x over y, x to y over z mod pz, for p is bigger than the fiber dimension plus 1, assume that this family lifts to a log smooth family over z mod p squared z, then E1 degeneration of Hodge to Dalam hold true for F. Okay, so this is the proposition 1.1. Okay, so then we like to see some application for this system of Hodge bundles. Okay. Okay. Sorry. Okay, so this 1.2. Positive and negative shifts from the Hodge theory. Okay, this is the first definition is due to Griffiths, a holomorphic vector bundle E over a complex manifold Y called semi-positive. If E carries a Hermitian metric whose curvature form, which is certainly a 1-1 type and a Hermitian, okay, which is this curvature form is semi-positive for any section from local section from E and for any holomorphic tangent bundle. C. Okay, this is a curvature definition by using curvature. Okay, and then we have also a global definition. So in the algebraic setting, this is mainly due to feedback. Okay, so let F be a torsion-free sheaf on a quasi-projective normal variety Y, H be an ample invertible sheaf, and U in Y be an open subvariety. First, F is called globally generated over Y if the natural morphism from the global section into F is surjective over U. Secondly, Y is called a weakly positive over U if the restriction F to Y is locally free, and if for any positive integer alpha, okay, then there exists some beta, such as positive number beta, such that the symmetric power S alpha times beta of F times H power beta is globally generated over U. This is certainly a generation. This weakly positive is certainly sort of a generation of I guess this is of semi-positive line bundle in some sense. Okay, the third definition is F is ample with respect to U if there exists some eta positive and a morphism from the direct sum of ample line bundle into the symmetric power eta of F is surjective over U. Okay, so okay, in short, we just call F weakly positive ample without referring open subvariety. We have some property for the weakly positive sheaf. The notion of weakly positive does not depend on the choice of an ample invertible sheaf and does not depend on the base changing on the generically finite morphism. Okay, if F is weakly positive and if F to G is a surjective over an open set of Y, then G is weakly positive. A tensor product of weakly positive sheaves with an ample sheaf is ample. Okay, so assume Y is projective, a numerically effective vector bundle F. It means that any quotient bundle of F restrict to any projective curve C in Y has no negative degree. It's weakly positive. So let's continue. Okay, example of semi-positive Hodge bundles. Okay, this is due to Griffiths. Given a system of Hodge bundles coming from the variant Hodge structure, then the first Hodge bundle EK, 0 is semi-positive. Hence, it is locally, hence it is weakly positive on a projective base. The Griffiths augmented line bundle, okay, gamma, okay, and defined in this way. Yeah, just by taking determinant of Hodge bound with some weight, okay, with some weight, is semi-positive. And it is strictly positive on an open set if the Tau-Henry map is generically injective. Okay, Kawamata generalized the result, the Griffiths results for the canonical extension case, okay, over a log base. For instance, EK, 0 arising from the canonical extension of variable Hodge structure over a log base is weakly positive. Okay, so now I like to talk something more about this kind of positive or negative results. In fact, Griffiths' curvature formula for Hodge metric and in general, Simpson's semi-stability for Higgs bundle carrying Yang-Mills Higgs metric allowed us to study the negativity of the kernel of Higgs field. Okay, so let's start with, okay, given a system of Hodge bundle, okay, we have the EPQ and the next term is EP minus 1, Q plus 1. Then we have the Higgs field, theta PQ. We're sending EPQ to EP minus 1, Q plus 1 times omega 1 log S. Then we look at the kernel KPQ. So we have the following proposition. I done some times ago. Then the Baba for some general case, and saying that the dual of the kernel is weakly positive. And I should remark that the proposition 1,5, this negativity of the kernel also holds true for the geometric situation over Z mod P square of Z. Okay, so I will mention this statement over characteristic. Okay. So let's schedule the proof. Okay. So okay, so the kernel is torsion free and subchief, and after a blowing up on the singular locus of KPQ, we may assume it is locally free. So we just now we want to show the KPQ dual is NEF. Okay, NEF. Okay, and NEF just means that it's restricted to any projective. The quotient of the restriction of any projective curve has no negative degree. Okay, it's just called NEF. Okay, so two ingredients in the proof. First is Griffiths, the curvature formula for the Hodge metric on U. And the second is the work by Schmidt, Katanen, Katmer, Schmidt, Kashwaha, and Steenbrink on variation of the mixed Hodge structure along the boundary divisor S bar. Okay, so let's start. The Hodge metric H has a singularities along S bar of logarithmic growth. Hence, the curvature current of this Hodge metric on the kernel of the Higgs field represents the Chern class of KPQ on Y bar. So then we need to compute apply the Griffiths curvature formula. Griffiths curvature formula reads that minus theta adjoint wedge theta and the minus theta wedge theta adjoint. Roughly speaking, the first term is positive, the second term is negative. Okay, so now you're restricting this curvature formula to the kernel KPQ. We find the conclusion, we find a consolation of the positive term. The positive term disappear. So therefore, the curvature form of the Hodge metric on the kernel become to semi-negative. The first term is semi-negative. The second term is the fundamental form of a holomorphic subbundle in a holomorphic vector bundle is always semi-negative. So therefore, we get the semi-negative. So this shows a special case for projective testing curve C in Y bar, and with Y does not contain does not be contained in S bar totally when it has the restriction of the dual of the kernel to C is semi-positive. In general, a curve in C can be contained in the boundary divisor S bar. So therefore, we can find a minima intersection of the components of S bar, just called S bar I. Okay, I is the multi-index. C contains S bar multi-index, but C does not contain in S bar J for any multi-index which contains I properly. Okay, so then we look at the multi-residual map on the Higgs bundle restricted to S bar I along the all component Si where I from the multi-index which defines a weight filtration on the Higgs bundle restricted to this S bar I. And it's restricted to also a filtration. It restricted to also a filtration on the kernel restricted to S bar I. So we just see this weight filtration. Okay, now such that this weight filtration has the property such that the quotient of this weight filtration lies in the kernel of the Higgs field on the gradient Higgs bundle on the polarized variable Hodge structure arising from the gradient of the weight filtration on the variation of mixed Hodge structure along S bar. So therefore, the proof just follows from the special case. So we have some immediately consequence from the weakly positivity of the dual of the kernel. Okay, this is proposition 1, 6. If you carry a generically injective period mapping phi from U to some period domain divided by the monotomic group, then the logarithmic canonic line bundle Y bar S bar is big. It means that it is ample with respect to some open set in Y bar. Okay, let's schedule the proof. First, the logarithmic one form is weakly positive. How can we see that? You look at the Higgs field from E to E, tensor the logarithmic one form, which induces a natural map of the Higgs bundles from the tangent, log tangent sheaf to the endomorphism of the given Higgs bundle. Okay, this is a Higgs map, and which of course coincides with the derivative of the usual period mapping over U. Let's assume the image of this map, image of the logarithmic tangent sheaf and as T bar. This T bar lies in the kernel of the Higgs field on the angle of E. So we therefore see that according to the proposition before, we know that E bar dual is weakly positive. But as the E bar dual is equal to the logarithmic one form on the open set, because the period map is generically injective, so therefore we get omega 1, and we get logarithmic one form is weakly positive. Okay, so second step to say the log canonical line bundle is big. Okay, we consider here's alternative proof. It's not the same as my original proof. Okay, this is shorter, I guess. We consider Griffiths augmented line bundle gamma on Y, which is big, as the period mapping is injective at some. One takes a suitable tensor product of the original Higgs bundle, right? Takes a suitable tensor product of the original Higgs bundle. We just call the ET theta T, such that the Griffiths augmented line bundle contained in the Hodge bundle in some pieces of this tensor product by construction. Then we can run in the maxima no zero iteration of Higgs map theta t with initial line bound gamma in this Hodge bundle, we obtain the so-called Griffiths you cover, okay, just around air time. Where you get the symmetrical power of log tangential tensor Griffiths augmented line bundle goes to, under this iterated Kodaira-dimension map, go to the kernel of the next step, because this is maxima no zero. Okay, so so we see that, okay, so okay, such that the image of the iterated map lies in the kernel. Take the dual of this Griffiths you cover coupling, we get the Griffiths augmented line bound tensor K dual, which is semi-positive, and under this power of the Kodaira-dimension map, which is not zero, but this is the first factor is positive. The second factor is semi-positive, so the altogether is positive. So we get ample line bundle into some symmetric power of log dimension form. But what is the quotient? Quotient is Q. But we know that the log dimension form is semi-positive. It's weakly positive. So therefore, the symmetrical power of a log dimension form is again weakly positive. Therefore, any quotient is also semi-positive. So therefore, you just take the determinant. You get ample line bundle in the canonic log canonic line bundle. So you get the proof. Okay. So any question? No question. So now I can. So now I should maybe I'm not sure. So maybe I okay. So maybe I should not to talk. Anyway, we have this kind of results. Okay, we also have this kind of semi-positivity or negativity results over characters P using periodic Higgs bound, but I think I should left this part away because this is not directly related to my talk today. I just leave this away. I just do the next part. Okay, so the 1.4, a greater Higgs bound from the deformation cell. Given a log smooth family, okay, a log smooth family, okay. What will happen if the all-Tau-Henle mapping associated to F become trivial? We have seen that if the Tau-Henle map is not trivial, we get certain negativity or positivity on the base, but it can happen, okay, in the praxis, all the Tau-Henle map become trivial. So now, in a joint work with the feedback, we start with the classical Kodaira-dimension map. Yeah, this is very classical Kodaira-dimension map. Yeah, and yeah, very classical Kodaira-dimension. I guess everybody know that. Okay, then we define then the extended Kodaira-dimension map. Just say tau PQ. This is just by taking the cut product of the first Kodaira-dimension map with the cohomology of high degree of tangent shift. Okay, you start with the first Kodaira-dimension map, tau and comma 0 time identity, right? Then we have here we have the two factors. One is first cohomology of the tangent shift, then tensor product with the Q's cohomology of the Q's power of the tangent shift. Then we can take the cut product, then take the wedge product, right? We get the composition. So therefore, we take the composed map, we get tau PQ. So we get the higher order Kodaira-dimension sphere, top Q. Now we putting all the individual shapes FTQ defined as the Q's direct image of the Q's power of tangent shift, okay, modular torsion. Okay, this is the bundle part of the shift part. And of course, you just by doing linear algebra, you can see that what is this shift? This shift is nothing, just the Q's direct image, Q's direct image of omega p relative p form, log p form, but twisted the top logarithmic differential form inverse. This is not exactly the Hodge boundary, but twisted the top log differential form of inverse. So this is then together with top PQ we get so-called deformation Higgs boundary, or just more precisely we should call this the sheet attached to any family. We just call this deformation Higgs boundary in short as F tau. When checked that this tau is direct sum of tau PQ satisfies the integrable condition tau wedge tau equal to 0, just using associativity and anti-commutativity of the co-product of double cohomology of tangent shift along fibers. So therefore, this F tau is really a graded Higgs boundary. Okay. So the system of Hodge boundaries we introduced in the subsection 1.1, and the deformation Higgs boundary play a central role in our investigation of global properties on the modular space of manifold. Okay, for example, let's look at a simple case. For a semi-stable family of abelian or Calabi-Yau manifold with maximal variation, we find a relation between the deformation Higgs boundary and the Higgs boundary arising from the variant of Hodge structure of the middle cohomology of the fibers. Just reading this form. Just simple do some simple computation. You see this relation. Okay, so where E theta is the variation of Hodge structure of this family of the middle cohomology, twisted with the Hodge boundary. Okay, in Calabi-Yau case and in the abelian variety case, in fact, this is so-called automorphic line boundary, which is ample on Y. Okay, you find this kind of relation. In generally, for a family of N-fold, N-manifold with no negative Kodaira-dimension, Kawamata feedback positivity theory and the direct image of the relative pluricanonic sheaf allows us to construct a no-trivial Higgs boundary between F tau and a system of Hodge boundary E theta arising from intermediate geometric situation. Okay, this is not exactly coming from the origin family, but coming from the certain cyclical color. Okay, where A is ample line bound on Y. Okay, so this is the goal we like to do in the next step. Next step. And okay, so let's do the next step, the comparison between deformation Higgs boundary and comparison of deformation Higgs boundary and the system of Hodge boundary. First, we just record the positivity of direct image shifts. Let F from Y from X to Y be a family of N-folds with semi-ample singular fibers, theta over S, and with the smooth part of the family, just call F from V to U. Okay, the following positivity of the direct image of the pluri-dualizing sheaf plays the fundamental role in study of the Ithaca conjecture. Okay, so this is a theory due to Kawamata feedback. Assume F from X to Y has the maximal variation, and omega V over U is semi-ample, then the direct image of Nu's power of this dualizing shift, relative dualizing shift, is ample with respect to an open subset for all V, all Nu bigger than 1, which is not vanishing. Okay, the fiber is not vanishing. Okay. So of course, the condition semi-ample is looked quite strong. In fact, Kawamata can pull for the family whose fiber admits a good minimum order, and the Kola pulled for the family of the fiber of general type. Okay, so I will mention the general form of this positivity results later. Okay, now by constructing the comparison map, we need actually a slight strong form of the positivity of the relative log differential form of the top degree. So you see that the relative dualizing shift in general is slightly bigger than this top relative top differential log differential form, okay, called L. Okay, so we have a small proposition. Again, the direct image of L power nu is ample for open subset U prime for nu sufficiently large. Okay, for ample line bundle A, for a given ample line bundle A over Y bar, by replacing the original family X over Y, do this kind of birational modification, birational modification of the base, and by self-product of a high power of original family, or by Kawamata base change, we may assume that L power nu tends to F up star A minus nu is globally generated over some open set on the total space. Okay, just doing by taking the fiber product of base change, we can raise the power of A. Okay, so now we are trying. I'm trying to talk about the comparison map, which is the crucial part in my talk. So let's do some motivation for this construction. First, we look at we look at the Hodge theory, cyclical cover, and vanishing theory, which is due to Ano, Fivek, and Kawamata, and maybe and some other people. Okay. One of the motivation of constructing the cyclical cover is trying to give a more Hodge theoretically proof of Kodaira, Akitsuki, Nakano vanishing theory. Okay, let X to be a projective manifold L line bundle on X with a section in the power of L. And let's assume D is a zero divisor of X. One takes a new cyclical cover, okay? We get a new variety Z, okay, as the cyclical cover, a new cyclical cover of X. Then you look at the direct image of the log form on the Z. It can be written in this form: direct sum of differential form back on the original variety and tensor L minus power I. The link has shown that this is a sort of E1 degeneration for the log differential form, shows that the open manifold, the cohomology of the topological cohomology of the open manifold is direct sum of the Hodge cohomology with log pole. Okay, so if D is ample, then the complement X without D is affine. The same holds true for Z without the pullback divisor. Hence, we have one theory of the topological cohomology for any K big than the complex dimension of X. Okay, complex dimension of X. So by Hodge decomposition, okay, so we by the Hodge decomposition, we know that this has to be 0 because we can use the direct image compute this Hodge decomposition downstairs. This is precisely the log-dimensional form on downstairs and twisted with L inverse. Okay, so therefore, for any P plus Q bigger than N, we have the vanishing theorem on the downstairs. Okay, this is a differential form downstairs, log differential form downstairs, twisted with L inverse. Okay, so using the residual map, okay, using the residual map and the induction on the dimension X, we show the Kodaira type vanishing theorem. Okay, anyway, this is, you look at, this is exactly in the range P plus Q bigger than N. This is the complex dimension of X, or small than the dimension of X. In contrast, the no vanishing theory of the middle dimensional cohomology, plays the crucial role in the construction of the comparison map in the next step. Okay, now we are going to do our comparison map, and this is done by Phil and myself some time ago. Okay, let's repeat again the notation. L denotes the top log dimensional form of the family X over Y. Okay, we know that by the positivity result, we know that this guy has a section for high power nu. Okay, so then we choose a generic no zero section S in this line bundle. This line bundle is divided by nu. So therefore, we can take a cyclical cover gamma here. Okay, then we take the composition. We get a new family G from the Z to Y, induced by this cyclical cover gamma, and with a singular fiber pi over S plus T, where T is a degeneration locus of the new singular fiber arising from this cyclical cover. By blowing up and leaving out codimension 2 substring of Y, we may assume this new family G from Z to Y is log smooth. Okay, take the E theta to be the graded Higgs bundle of the quasi-canonic extension of variable Hodge structure of the middle cohomology of this new family. Then we claim there exists a Higgs map from F tau, this is a deformation Higgs bundle, to the system of Hodge bundle twisted with A inverse. What does mean that? This means that we have such kind of commutative diagram. The Higgs map, tau PQ and theta PQ is commutes with this rho PQ, okay? Where eta is canonic inclusion from the log form with log pole along S bar to the log form along the pole S bar plus T bar. Okay, we should do some remark. Note that the comparison map rho PQ is defined only on Y a priori. That is a morphism between FPQ to F bar PQ restrict to Y and EPQ equal to EPQ bar over Y. Okay, where F bar PQ is reflexive. Okay, this is defined over Y bar, which is reflective, and the codimension of Y bar without F, without Y is bigger than or equal to 2. So therefore, the comparison map automatically extends to Y bar. Okay, so we also should emphasize the push point in the comparison map. Although the Higgs field on the new Higgs bundle has singularity along S bar plus T bar, the restriction to the image of the comparison map of the deformation Higgs bundle has only singularity on the origin of degeneration S bar. This means that this in this new construction, this new degeneration locus T bar has no effect to our original geometry picture. Okay, so okay, so let's do. Maybe I should schedule the construction. Okay, first choose a generic no-zero section as before, such that the zero divides the D. Okay, intersect the generic fiber of F is smooth. Let D in Y denote the locus of the discriminant of the map D restricted to V to U, which is precisely the locus where the intersection D intersect with the fiber become singular. Okay, so let the sigma to be the fiber over this degeneration locus T. Okay, then you do some blowing up. After blowing up, we may assume blowing up with the center in D, and in the original, this is the original singular fiber of F. This is new fiber over this degeneration locus T, and leaving out some codimension 2 subscheme. We may assume the pre-image on this blowing up of D plus delta plus sigma is normal closing, and the composition map Y prime, this is the family, X prime over Y is log smooth as a morphism between the log pair. So the next step is to the cyclical cover by S. Okay, we just do the pullback of the line boundary to the blowing up. Then we just do the cyclical cover on the X prime. Then we have to take some normalization, Z prime, but this normalization Z prime could be still singular. Then by taking the resolution of singularity of Z prime and blowing up at the center of the fiber of Y, it become a new singular variety Z, and a generic finite map eta. And leaving out codimension 2 subscheme of Y, we may assume the induced map is log smooth. Okay, so sorry here, log smooth. Okay, the third step, we calculate the differential form on the cyclical cover. Okay, so recall that the local system of the variation of the middle cohomology of the new family G, just writing this form. Okay, blah blah from the V to V tensor, the differential form with log pole S plus T as a quasi-canonic extension. Okay, we get this kind of featured logarithmic dilemma bound as a quasi-canonic extension of this local system. Let E theta denote the induced system of Hodge bound. Okay, so according to proposition 1.1, we know that we can compute this EPQ in this form. Okay, so and the Higgs field theta PQ is the connecting map of the direct image applied on G of the exact segments. Okay, so and we also consider the pullback of the deformation of the Higgs bound F tau on Y with the blow up. Okay, you have this kind of form. You have this kind of F prime PQ in this form. And we know that Kodaira-dimension map is also defined as edge morphism of the direct image of F prime lava star of these short exact segments. Okay. So let's this black point, and denote as spectrum C of Y, then the Galois group of the cyclical cover acting on the differential form of the direct image of differential form, and with eigenspace decomposition. Okay, which induces a natural inclusion from this differential form to the direct image of the second type dimensional form. Okay, it just coming from the natural inclusion. Then you take the pullback. We proceed, and the inclusion 1.3.3 with the inclusion of the locked dimensional form induces exact sequence of pullback of 1.32. 1.32 is here. Pullback of this. This define our the cohomology of this exact sequence define our locked dimensional form. Okay, then we get to this inclusion, and this short exact sequence define the system of Hodge boundaries. Then we take the direct image of the G upper star, G lower star. So this yes, exactly the comparison path we are looking for. Here, FPQ is a deformation Higgs bundle, and this EPQ is the system of Hodge bundle arising from the cyclical count. Okay, and this map is by construction is commuting with the Higgs field as an edge connecting map. Okay, so then okay, so we still have some minutes. Okay, let's talk about the property of the comparison map. Okay, so we have this kind of comparison map. We have this kind of comparison map, and we like. Sorry, we just see. So we have this kind of comparison map. We like to say this comparison map is no trigger. If this map is 0, so we get nothing, right? So let's explain that. Okay, so this is a sort of Toheli injectivity. Firstly, the first comparison map is injective. Okay, and if the canonical line bundle of the fiber is ample, then every rho PQ is injective. Okay, so therefore you get really F tau inclusion as shift map. Okay, so the third case, if the canonical line bundle of the fiber is big, then the second comparison map is injective at all points. Okay, this is some weak statement if the canonical line bundle is big, but not ample. The third case, the fourth case is very general case. If the canonical line bundle on the fiber is semi-ample, then the following comparison map, comparison map is injective. Okay, this map, the comparison map, this map is injective. Okay, so the pool is just using Kodaira running theory or Bogomolov running theory. In the fourth case, this is the general case. Feedback flow has shown a weak form. Okay, we just show this map is not 0, but we don't know if this is a pointwise and injective and along any direction. And then yeah, obtain the full statement in the proposition 4, basically using the Griffiths curvature formula and the positivity of the curvature of A pointwise. Okay, so you get the pool. Okay, so okay, so now we as application of this comparison map, we like to show some symmetrical power of differential form on the base containing an ample subshift. This is quite similar to the situation where we have Tahelli injectivity. We use the Griffiths augmented line bundle to produce this ample subshift in the symmetrical power of omega 1. Here is quite similar. We look at the sub-Higgs shift of this comparison map, just called G theta G. Note that the first Higgs bundle of this subshift G theta is still trivial line bundle, and theta G has logarithmic pole only along the origin boundary device as well. So the Tahelli injectivity position 1.4 allow us to run the maxima no-zero iteration of the Higgs map on this sub-Higgs bundle. You get in this form. So this is so-called Griffiths Yukawa coupling on the deformation Higgs bundle. We have shown that this guy is semi-negative, right? By doing the Griffiths curvature computation on the system of Hodge bundle with respect to the Hodge metric. So the dual of this kernel give you semi-positive subshift together with A. We get this. This is strict ample on opens. This is ample, and this is a semi-positive. So therefore, this is okay. Therefore, we get an ample subshift in the symmetric power of differential form. Okay, I guess I should stop here, and I should tomorrow to talk about the application of the existence of this ample subshift. Okay, let me stop here. Okay. So thank you.
Okay. Yeah, thank you, Kang, for very nice talk. And I wonder if there are any comments or questions anyone would like to ask. One question I had is going back to the Kawamata.
Kawamata. Okay, let's
the
let
positivity of the direct image of the relative dualizing sheaf. And if you assume local Torelli property, that direct image is actually in some way ample.
Yes.
On the other hand, if you take instead of the relative dualizing sheaf, just the relative sheaf of one forms, logarithmic one forms on the total space, then the direct image has some positivity, but it, I think, can almost never be ample. Or is there any...
Okay, let's go. Sorry, let's go to the. You mean to the Kawamata's? Okay, yeah, let's go. Okay, so let's see. Okay, let's see. Okay, you mean here the Kawamata's result?
The Kawamata, he proves that the direct image of the relative dualizing sheaf.
Okay. Okay, let's go. Okay, I know where is. Sorry. Okay, so here you here.
Yeah, he proves some ampleness for that. He and Vivek. On the other hand, if you take the direct image of not the relative dualizing sheaf, but the relative one form, so that's not a line bundle upstairs, it's a vector bundle. That has positivity, but I think it's almost cannot be ample. And I wondered if there are results you know of about the extent to which it fails to be ample. There's some geometric constraints that some flatness, if you like, of the direct image of the relative one forms. Do you know anything about that, or is there literature about that?
Yes, let me try. Okay, you ask replaced by dualization by the big omega one, bigger.
That's right. Yes.
You mean right? You mean this guy, right?
Yeah.
Yeah. Okay. Certainly, this is the semi-positive. This is just again apply your theory on the semi-positivity of the. This is a weight one. Weight one. This is a system of Hodge one of weight one. So you see, this is in any case, this is a semi-positive. But you ask if this is ample. This is a good question. I would guess he should never be ample except the fiber is a curve. But
okay.
But just my feeling. But at the moment I do not know how to prove that. But yes, this is a really good question. But yes, this is a really good question. At the moment, I really do not know how to put that, but this is a really good question. Yeah.
Okay. Yeah. Any other question or comment? So once again, I'd like to thank the speaker for a very nice talk. And the next talk will be at 1 o'clock, an hour and a half, or a little less than 1 hour and a half from now. So thank all of you for logging in, and we will see you in 1 o'clock.